Hello, dear students. Welcome to the fifth lecture of the lecture series on machine design. In the previous lecture, I have explained to you the design of parallel fillet joint as well as transverse fillet joint. We have seen that the parallel fillet weld fails across the minimum cross-sectional area because of shear stresses. On the other hand, transverse fillet weld fails across the minimum cross-sectional area because of tensile stresses. However, the nature of stresses in the cross-section of the transverse fillet weld is quite complex. The weld is subjected to normal stress as well as shear stress. Besides, the throat is subjected to a bending moment which adds to the complications. Theoretically, it will be proved in this lecture that for transverse fillet weld, the inclination of the plane where the maximum shear stress is induced is 67.5 degrees to the leg dimension or to the horizontal. To simplify the design of fillet weld, many times shear failure is used as the failure criteria. It is assumed that stresses in the transverse fillet weld is shear stress on the throat area for any direction of the applied load. With this assumption, load equation derived for the parallel fillet weld can also be used for the transverse fillet weld. So if you assume that the stresses acting in the transverse fillet weld are purely shear, then with this assumption you can apply the load equations derived for parallel fillet weld to the transverse fillet weld irrespective of the direction of the applied load. Both types of welded connection fails across the minimum cross-sectional area, which is T times L, where T is the throat and L is the length of the weld. And then in the previous video I solved some related problems. In case you haven't seen that lecture, you will find a link to that lecture on your screen at the top right corner. Click on that link and watch that lecture before this. It is highly recommended that you watch the lectures in the proper series. That is, first you watch the first, then second, then third, and so on. Secondly, some of you have posted your questions in the comments box below, to which I have replied. I hope that answers your question. In case anyone still have a doubt, do let me know or comment in the comment section below. You can see that this lecture is on maximum shear stress for parallel and transverse fillet weld. In this lecture, I'll explain to you how to find the inclination of the plane inside the weld where the maximum shear stress is induced and the magnitude of the induced shear stresses. This will be done for both types of fillet weld, that is for parallel as well as for transverse fillet weld. By the end of this lecture, you will see that the inclination of the plane where the maximum shear stress is induced is inclined at an angle of 45 degree and 67.5 degrees respectively for parallel and transverse fillet weld with respect to the horizontal plane or the leg dimension. In this figure over here, you can see that a double parallel fillet weld is shown. This is your first, just a minute. This is your first fillet weld, parallel fillet weld, and this is your second parallel fillet weld. So a connection or a structure is shown which has double parallel fillet weld. and the length of the weld is equal to L. Since the direction of the force which we have applied is parallel to the direction of the weld, that's why we are calling this type of weld as parallel fillet weld. Now this structure is, or this plate assembly is subjected to a compressive load of magnitude 2p. It is subjected to a compressive load. Now this area over here of double parallel fillet weld can be seen in an enlarged view. Okay, this is basically the cross-sectional view of both the fillet welds. Here you can see a symbol X is shown, and then you have two dots. Okay, these symbols have some meaning. This X symbol is basically drawn at a place where we have to show a force parallel to the plane, but moving away from the observer. It is moving away from the observer. This force X is moving away from the observer. Now the other type of force which has been shown in this figure is a dot. This is again perpendicular to the screen and moving towards the observer. It is moving towards the observer. So this is a force, this X is a force of magnitude 2p perpendicular to the plane moving away from the observer, whereas these two dots are the reaction force, again perpendicular to the plane but moving towards the observer. Okay, so always keep in mind these notations. Now the reaction force are obviously of the magnitude p, because you have applied a compressive load of magnitude 2p on the structure. Now this line over here shows a plane which is inclined at an angle of theta with the leg dimension. This plane is inclined at an angle of theta with the leg dimension, and we are assuming that this is the plane where the maximum shear stress is induced. So we have taken an inclination of theta with the leg dimension where the maximum shear stress is induced. Now the idea is to find out this inclination and then the induced maximum shear stress on this plane. Okay, so initially we have assumed that this plane is at an angle of theta with respect to the leg dimension. Secondly, don't confuse this T dash with T. T was a plane which was inclined at an angle of 45 degree with the leg dimension, and T multiplied by L is giving you the minimum cross-sectional area. But this T dash is completely different. This is the inclination of a plane where the maximum shear stress is induced, which we have assumed as theta. So this theta we have to calculate. It might be 45 or it might be something else, but since it can be any value, that's why this T dash is completely different from T. So don't confuse it with T. T was the inclination of the plane at an angle of 45 degree with the leg dimension. Secondly, you can see that the weld is basically having a cross-sectional area of in the shape of isosceles right angle triangle, which means that this side is equal to this side, and since this angle is 90 degree, that's why we are calling this complete triangle as isosceles right angle triangle. Since this side is equal to this side, and this angle is 90 degree, which means that these two angles are 45 degrees. These two angles are 45 degrees. In the previous lecture, I told you that the cross-sectional area for the fillet weld can be in the shape of concave, or it can be in the shape of isosceles right angle triangle. And then I also told you that because the stress concentration in this case is much low, that's why we always go for this type of cross-sectional area. Now this figure over here shows you an enlarged view of the cross-sectional area, which is again an isosceles right angle triangle. Triangle A, B and C shows you the cross section of a single parallel fillet weld, where angle ABC is 90 degree, angle BAC is 45, this angle is 45, angle ACB is again 45 degrees. Now since DE is perpendicular to BC, that's why this angle again is 90 degree. which makes this angle CDE again 45, because angle E is 90°, angle C is 40, and angle C is 45°. That's why angle D will also be 45°. Since angle EDC is equal to angle ECD, which is both 45°, these both angles are 45°, which tells us that the line DE is again equal to EC, and this triangle DEC is a right angle isosceles triangle. Now the leg dimension, which is H, is equal to BE plus EC. Okay, it is equal to BE plus EC, and since EC is equal to DE, that's why we can say that the leg dimension H is equal to BE plus DE. Okay. Now once again I'd like to remind you that the leg dimension as a rule is always taken as equal to the thickness of the plate. Now suppose you are having two different plates with different thicknesses. The thickness of this plate is thicker than this plate. This is your plate number 1 and this is your plate number 2, but this plate number 2 is thicker than plate number 1. Then in that case, if you are going to weld these two plates together, then in that case you will take the leg dimension equal to the thickness of the thicker plate. Okay, you will take the leg dimensions equal to the thickness of the thicker plate. Now this geometry will be more clear to you in the next slide. You can see that this is again the same figure, which is having triangle ABC, a right angle isosceles triangle. If you consider this triangle, you can see that AB is equal to BC is equal to H, and since these two lengths are equal, that's why we are calling it as isosceles triangle. Angle ECD is 45°, that means this angle is 45°, and DE is perpendicular to BC. DE is perpendicular to BC, which will make this angle also 45°. So angle EDC is 45 and angle ECD is also 45°. Now if you consider this leg dimension H, this is equal to BC. This is equal to BC, which in turn is equal to BE plus EC. BE plus EC. Now since angle D is equal to angle C, which makes triangle DEC an isosceles right angle triangle, that's why your leg dimension H is equal to BE plus DE. We have written DE in place of EC because these two lengths are equal. Now BE can be written as BD cos theta. It can be written as BD cos theta because this angle is theta. Okay, so BE is BD cos theta, and likewise your DE is BD sin theta. So it can be written in the form BD in the brackets cos theta plus sin theta, and this BC was equal to H. So H is equal, and your BD is equal to T dash. Okay, your BD is equal to T dash. In the previous slide you have seen that your BD is equal to this length is equal to T dash. Okay, so H, from these relations we can derive a relation which is H, which is the leg dimension, is equal to T dash. T dash is on the plane with an inclination theta, and we have assumed that this plane is basically having the maximum shear stress, multiplied by sin theta plus cos theta. If we rearrange some terms, we will have the value of T dash as H upon sin theta plus cos theta. T dash is equal to H upon sin theta plus cos theta. Now again, always remember that this plane which we are talking about is inside the weld, which is very obvious because we are interested in finding out a plane which has maximum shear stress within the weld. So that's why this plane is also inside the weld. Anyways, moving further, if you recall my video, whose link is again given to you at the top right corner, the video whose title is Design of Fillet Weld, you will recall from that video that the allowable shear stress is equal to the load applied on the plates divided by T dash into L. And you can see that I have taken only P over here, whereas the compressive force which was applied on the structure was of magnitude 2P. But since there were two parallel fillet welds, so each fillet weld will take a load of magnitude P. That's why I have written P over here. And T dash L is basically the cross sectional area of the plane which we are talking about. Now, if you will put the value of T dash from the previous equation in this figure, in this equation, you will have an equation like this, which says that tau, or the allowable shear stress, is equal to the load applied multiplied by sine theta plus cos theta upon h into L, where this is the cross sectional area of the plane which we are talking about. Now, in order to find out the inclination of this theta where your shear stress is maximum, what we will do, we will differentiate this equation with respect to theta and then equate it equal to 0, and then we will equate it equal to 0. So in these equations you can see that I have differentiated this equation, this above equation, with respect to theta, and then equated it equal to 0. From this equation I'll get the value of theta as 45 degrees. So 45 degree is the inclination of the plane where the maximum shear stress is induced in case of parallel fillet weld. Okay, this is the inclination of the plane where the maximum shear stress is induced in case of parallel fillet weld. Now, if you will put the value of this theta in this equation, you will get the magnitude of the maximum shear stress which is induced on this plane. So putting the value of this theta in this equation, in this above equation, we get tau max equal to the load applied, which is P, divided by 0.707 times h, which is the leg dimension, times L, which is the length of the weld. Okay, so this is how you are going to find out the inclination of the plane where the maximum shear stress is induced and the value or the magnitude of the induced maximum shear stress. Okay, so all these calculation is only valid for parallel fillet weld. For the transverse fillet weld, we have to approach in a different way. Now we will try to derive the same for the transverse fillet weld. Figure here shows you a transverse fillet weld or double transverse fillet weld. This is your first and this is your second transverse fillet weld. Since the direction of the force is perpendicular to the direction of the weld, that's why we are calling it as transverse fillet weld. Again, the length of the weld is taken as L, and this structure is subjected to a tensile load of magnitude 2P. It is subjected to a tensile load of magnitude 2P. Now in this derivation we will make an assumption that the effect of the bending on the welds are neglected. Our derivation is based on an assumption that the effect of the bending on the welds are neglected. So coming back to the derivation, this structure is subjected to a tensile load of magnitude 2P and the length of the weld is L. Now the cross section of these welds are shown in this figure in an enlarged view. Over here you have a tensile load of magnitude P. Because of this tensile load of magnitude 2P, there will be a reaction force in case of both the welds, and whose magnitude will be P and the direction will be vertically downwards. Since the load on the structure which is applied is of magnitude 2P and the direction is vertically upwards, that's why each weld will be having a load of magnitude P acting vertically downwards, like this in this weld, and over here like this in this weld. Now again we have assumed a plane with an inclination of angle theta with the leg dimension. This is a plane which is inclined at an angle of theta within the weld with the leg dimension. Now since this plane is having the maximum shear stress, so again we have to find out this inclination theta and the magnitude of the maximum shear stress induced in this plane. Now the forces which are acting in the weld are PS. PS is basically a shear force acting inside the weld, and a force perpendicular to the shear force which we are calling as PN, or the normal force. PN is your normal force and PS is your shear force. Both the forces are perpendicular to each other. This PS, or the shear force, is parallel to the plane which is inclined at an angle of theta where the maximum shear stress is induced, and the normal force PN is perpendicular to the shear force. The resultant of both the forces is P, which is acting vertically downwards. This force P is basically the resultant of this force PN, or the normal force, and the shear force. So you can see that since the resultant of this force Pn and Ps is acting vertically downwards, therefore the horizontal components of Pn and Ps are equal and opposite in nature. They are both equal and opposite in nature. Over here you can see that again the cross section of the weld is in the form of right angle isosceles triangle. And in this figure you can see the enlarged view of that triangle, which with this side equal to this side, and the dimension of these two sides are equal to the leg dimension, or h is equal to the leg dimension, or h. Again in this case, this length t dash, this is your length t dash, and it should not be misunderstood with t. T is completely different. T was the length where the angle of inclination was 45 degree. Here we don't know what is the angle of inclination, that's why we have taken it equal to theta. We are going to find out what the value of theta is, and that's why we have taken this distance equal to t dash. Now an enlarged view of the forced body, free body diagram, or the forces, is shown over here. This figure shows you the forces acting inside the weld. These are the forces acting inside the weld. Now you can see that PS is the force acting at an angle of theta. PS is a force acting at an angle of theta with the leg dimension, and this is parallel to this force PS is parallel to basically to the plane which is inclined at an angle of theta. That's why it is inclined, again this force PS is inclined at an angle theta with the leg dimension. The second force which is acting is a normal force which is perpendicular to the PS, and this force again is at an angle of theta with the vertical plane. This force again is an angle of theta with the vertical plane, because this force is perpendicular to this force, so this complete angle is 90 degree, and this is your angle theta, this is again 90 degree, which makes this angle 90 minus theta. This angle is 90 minus theta, and since this complete angle is theta, which makes this angle as theta. So your normal force is acting at an angle theta with the vertical plane. Okay, now the next thing is the resultant of these two forces is again acting vertically downwards. Okay, it is acting vertically downwards. So this is your force PS, which is parallel to the plane which is inclined at an angle theta. This is your normal force which we are calling as PN, and the resultant of both these forces are acting vertically downwards. Therefore I am saying that the horizontal components of the force PS as well as PN are equal and opposite in nature. They are equal and opposite in nature, therefore they are both cancelled out by each other, and the resultant of these two forces vertically downwards. Now let's start with our derivation. let's talk about the let's talk about the vertical components of the force PS and PN. Let's talk about the horizontal components of the force PS and the vertical components of the force PS and PN. So this equation written over here gives you the vertical components of the forces PS and PN, and we are equating it to 2P, which is acting vertically upwards. This force 2P is basically applied on the structure and acting vertically upwards, whereas these two forces 2PS sine theta and 2PN cos theta are the vertical components of the forces PS and PN, or of the forces or of shear force and normal force. Since we are having two welds, that's why we are having 2 multiplied by this value, or the vertical components of the force PS, and then we have again 2 multiplied by the vertical components of the force PN. This is because we are having 2 different welds. Now we have basically cancelled out 2 from this equation, and we are having this equation which says that P is equal to PS sine theta plus PN cos theta. Now the idea is basically to write down an equation for shear stresses in terms of theta, and then we are going to differentiate that equation with respect to theta, and then in order for us to find out the maximum in order for us to find out the inclination of the plane where the maximum shear stress is induced. But before that, we have to write the equation in terms of PS only. So first of all, we will try to relate the forces PS and PN, and this will be possible when we are going to equate the horizontal components of the forces PS and PN, since they are both equal and opposite. That's why we can write this equation which says that PS cos theta, which is the horizontal component of PS, and PN sin theta, which is again the horizontal component of PN. Now from this equation, if we rearrange the terms, we will get the value of PN in terms of PS. We will get the value of PN in terms of PS. Now again consider this equation and put the value of PN in this equation in terms of PS, so that we have an equation only in terms of PS, like this. Okay, we have an equation which is telling basically, which is giving us the strength of the weld in terms of only PS. So what we have done, we have substituted the value of PN in this equation to get this equation. Okay. Now moving further, in the previous derivation, or before that, what we will do, we will multiply this equation with sine theta. We will multiply this equation with sine theta on both the sides. So we have this equation which says that P sine theta is equal to PS sine square theta plus PS cos square theta. Okay, what we have done, we have multiplied this equation on both sides with sine theta. So we are left with the value of PS is equal to P sine theta. The value of PS, or the shear force acting inside each weld, is equal to P times sine theta. Now from the previous derivation, we can take the value of T dash, which is equal to H, or the leg dimension, divided by sine theta plus cos theta. This value we have taken from the derivation of parallel fillet weld, and since the cross sectional area for parallel fillet weld as well as for transverse fillet weld is right angle isosceles triangle, that's why this relation is valid for both the cases, which is for parallel as well as for transverse fillet weld. Now again, the shear stresses inside the weld is equal to the shear forces acting inside the weld divided by the cross-sectional area, which is T dash times L. Now what we will do, we will substitute, just a minute. What we will do, we will substitute the value of P dash from this equation in this equation, and the value of T dash from this equation in this equation, and we will get an equation which will look something like this, So your shear stress inside the weld is equal to P sin theta times sin theta plus cos theta divided by H times L. Now our idea in the beginning was to write an equation for shear stress in terms of theta, so that we can differentiate this equation and equate it equal to 0 in order to get the value for theta where the maximum shear stress is induced. What is theta? Theta is basically the inclination of the plane with the horizontal or the leg dimension where the maximum shear stress is induced. So we will try to differentiate this equation and equate it equal to 0. And when we equate it equal to 0, we will get the value of theta as 67.5 degrees, which is same as which I told you in the starting of this lecture. So for your parallel fillet welds, the inclination of the plane where the maximum shear stress is induced is 45 degrees, whereas for transverse fillet weld, the inclination of the plane where maximum shear stress is induced is 67.5 degrees. Now we will put this value of theta in the previous equation of which is basically giving us the relation between shear stress and theta in order to get the maximum shear stress, because this is the inclination where the maximum shear stress is induced. So the value of maximum shear stress in case of transverse fillet weld is 1.21 multiplied by P divided by H into L, where P is the load acting on the structure, H is basically the leg dimension, and L is your length of the weld. So this is your the inclination of the plane where maximum shear stress is induced, and this is the magnitude of that maximum induced shear stress. So this was all about this lecture, and in the coming lecture I will explain you the basically the design of axially loaded unsymmetric weld. Now suppose this is a plate, okay, this is a plate. Now till now you have studied the design of the weld, where suppose we have welding over here as well as here, okay. So till now you have studied the design of a weld where the length of the weld at the top is equal to the length of the weld at the bottom. But in the next lecture I will teach you the design of the weld where they are axially loaded and the length of the weld at the top is not equal to the length of the weld at the bottom. Or I'll teach you the design of the axially loaded unsymmetric weld. And after that we will try to solve some problem on that for axially loaded unsymmetric weld. So thanks a lot for listening this lecture patiently, and I'll see you in the next lecture. Thank you.